So, welcome, good evening, or good morning. As you can tell, I'm not here to help you out. Today, my grade 11s, once again, here is a quick lesson on section 4.7. I would call it solving exponential word problems. I'm going to try to go through the 5 examples from your package. Again, please feel free to pause the video if you need some help. And, we will still have time to answer questions. Furthermore, I have given you an additional handout. Hopefully the supply teacher has given this out. I kind of like my handout because it talks about our word problems in a different way with some formulas, which you might see when I take it up. Now, if you're a little confused, don't worry. However, this might be a little long video, so again, feel free to pause, rewind, and just follow along. And of course, you can ask me questions on Friday. Anyways, let's get to it. Let me share my screen again. Hopefully this recording is fine. I had some problems with my other glass. Let's just see this is the right one. I think this is the surface panel. So hopefully you can see on your screen the applications involving exponential functions. So let's just get rid of my face too, because it's kind of weird. Turn off the video. Let me just zoom in. Also detach. Let's get started. Exponential growth and/or decay occurs when quantities increase or decrease at a rate that's proportional to a quantity present. Some examples of exponential growth are savings account, so that's related to our financial math, inflation, and even population size. Exponential decay is really also another way that things devalue, also known as depreciation, also known as maybe radioactive material decay. So I scroll down here really quickly. You can see that the, oops, let me move this. The formula we have is f at x equals a times b to the x. Now, a in this example stands for the initial amount or number. This is also known as the principal. And we'll talk about this more when we go through things. Now, the b, a lot of you saw me in our notes that b is our base. And whenever b is greater than 1, it actually means a growth. In these word problems, we will see when b is added to the growth rate, which is usually a percentage, so 1 plus that growth rate, or a decay rate. And a lot of you understand that when you have a decay rate as a percentage, that base will be smaller than 1. So let's take a look at this first question, and I'll help you guys out with it. This is classified in my handout that I'm giving you today, not from the workbook, as a general exponential word problem. If you put $1,000 in the bank at 8% compounded annually, how much do you have in 25 years? So the formula we're going to be using is y is equal to a times b to the x. Now, I must warn you, when we solve a lot of these questions, a big mistake is that some students will multiply a times b. But you have to kind of remember that that exponent kind of takes precedence. So let's talk about things. I think everyone agrees. The a value is the initial amount. So that is our $1,000. The 8%, that seems to be the growth rate. Now, as 8%, you change it to a decimal, so it's 0.08. Thus, the b value, or the base, I think a lot of you understand, and if you looked at what I boxed, that's why I kind of kept it there, that b value is going to be 1 plus 0.08, which of course really means that the b value is going to be 1.08. And many of you actually understand this because in grade 9, hopefully you learned about taxes. And when I say taxes, we're talking about maybe like the HST, and you tend to add 1 to the harmonized sales tax. And then you multiply by the original amount, and that gives you the new amount that you're going to pay in total. It's kind of like the same idea. So in this case, the 25 years represents the time period. So this represents our exponential. So when we actually plug in everything that we have, what we'll get is y, which is the new amount, is equal to the initial amount times the growth rate to the 25. You have to use our calculators. And I'm just going to show you. Hopefully you can see this on your screen. We actually have to do 1.08 to the 25. Now you don't have to go this slowly, but we're going to get this answer. And I'm just going to hopefully write this out. Hopefully it's going to pop up again. And I apologize. I will have to take a look at the screen. That's 1,000 times 6.84847. And it keeps on going. So when we multiply this by 1,000, our final answer to 2 decimal places, because in Canada, we round to the nearest cent, we get $6,480.48. So this money is called compound interest, and I wish we had more time when we talk about it later in our final unit called financial math. So how much would you have? We would have 6,800. Oops. Let's try that again. $6,848.48. A lot of you realize this is a lot of calculator work. Question 2. A new car costs $24,000. Its depreciation rate is 18% per year. Determine the value of the car after 2 years. So just to give you words of interest that's relevant right now in today's society, a lot of the new cars right now are almost, or if not on par of the used car market. So just to share with you, a lot of used cars have actually grown in value. So they actually have appreciated. So depreciation is really what happens, and historically, when you drive off the lot, your car is literally not worth as much as soon as you take ownership. So in this example, what we realize, we're still using a generic exponential setup. I think everyone understands that the initial amount is 24,000. Notice the decay rate is 18%. And of course, 18% as a decimal is 0.18. But because it is depreciating, and I apologize, I'm not going to scroll back up, our B value is going to be 1 minus this decimal, which of course equals 0.82. Notice this base is between 0 and 1. So you know this is not a growth, but it's going to be a decay. Finally, what is our x? And I apologize, I didn't do it for the first question. Our x of our years is that 2 years. So plugging in the information, we want to find the new amount, and it makes sense that the value of our car is probably going to be less than 24,000. So we plug that in, plug in the base, plug in that too. Pause the video if you want to try it yourself. Again, we have to do the exponent first. So I'm just going to quickly pop this up on our screen. And notice I will actually enter it this time directly. 24,000 times 0.82 to the exponent of 2. Pause the video if you want to try it yourself. If you're using the school calculators, I'll probably have to help you. But if you understand how to use the school calculators, you'll have to do the 0.82 first, then square it, then multiply that answer by 24,000. And we should get this answer of $16,137.60. So notice a lot of these word problems right now are pretty straightforward. So the value of the car, and I know it's shocking, is worth only $16,137.60 after 2 years. Let's take a look at example 3. Now, example 3. A used car dealer sells a 5-year-old car for $4,200. What was the original value of the car if the depreciation rate is 15%? This one's a little bit different, a little bit more challenging, but I think a lot of you can understand what we're going to be going through. I think everyone agrees. This represents the time frame. So our X value is 5. Our depreciation value rate is 15%, but it is going to be a decay. So 15% is 0.15. That means our B value is going to be 1 minus 0.15 because of the depreciation, which means B will be equal to 0.85. But notice the original value represents our A. So we're trying to find what A is. That kind of means then this 4,200, that's going to be our answer, or Y. So this question is kind of like working backwards. To set this up, we're probably going to get 4,200 is equal to A times 0.85, which was our base, to the 5. Using some rearranging, a lot of you realize I can actually just change this up. The A value is going to be 4,200 divided by 0.85 to the 5. So this is just a manipulation of the formulas. And a lot of you understand this because the opposite of multiplication is division. So taking our calculator, and hopefully you're seeing this. I really hope this is working this time. We're going to take that 4,200 and we're going to divide it by 0.85. That's going to be raised to the 5. One more time. If you're using the school calculator, you might have some difficulty of actually entering this in. So I hope you have one of our calculators or the calculator I recommend. And this is the Sharp EL510RN calculator. Press equals. And it kind of makes sense is that the original amount, oops, I made a mistake. Let me just double check. Oh, that's right. Sorry. No, I looked at the decimal wrong. I thought I made a mistake. So it makes sense that the new amount should be more than 4,200. So the price of the used car was $9,465.85. So the original value was $9,465.85. Okay. Our fourth example. I tend to teach this as a half-life problem. Let's read it. Half-life is the period of time during which half the mass of a radioactive element may decay. An isotope known as strontium-90, SR90, has a half-life of 25 years. Find the mass of strontium-90 remaining after 195 years from an 18 milligram sample. So although you know this as a general exponential equation, on the supplementary handout that I've given you, it might look a little different. We're going to just change this up. Y will still be the new amount of whatever we're working with. The A is our initial amount, which will be the larger than the new amount because this is a decay problem. Notice that our base will be a half, and I'll explain that in a moment. And our exponent, which is our time, will represent the time period divided by the half-life period. So this formula is called the half-life equation. Now, it might look different on the other handout, and I'm sure many of you can see the M's or the C's that we have. They're just replacing of the Y and the A respectively. Hopefully I said that correctly. Anyways, let's try to decode this word problem. So I think the half-life period is represented by that 25 years. Hopefully you can all see this purple. The time period, though, that we're actually going to use is actually representative of 125 years. And the original amount is going to be 18 milligrams. So using our formula, y is equal to a to the half t divided by h. We want to find the new amount, which is going to be equal to 18 times the half, which is our base, to the 125 divided by that 25. And just pause the video if you're not too sure how we're subbing in. Notice that exponent represents the time frame. So we have to take that time frame that's divided by the half-life. And again, using our calculator, I'm going to do this one slower, if that's okay. And just make sure I got this right. We're going to get y, oops, I'm still in purple. I should change that back to black. We're going to get y is equal to 18 times 1/2 to the 5. And again, using our calculator really quickly, notice again, maybe I'll do this one slower. 1/2 is 0.5 to the 5. We get this really small number. So y is equal to 18, whoops, times 0.03125. And then times it by 18. And so after 125 years, the new amount of the strontium-90 isotope will be only 0.5625 milligrams. So notice, it has decayed a lot. For final example, and don't get me wrong, on Friday's class, I'll try to do some of those questions on the extra handout. Question 5 is interesting. If you're taking SAP, this might be interesting to some of you, or anthropology, sociology, and anthropology. I think I might have said that. Sorry, I'm a little tired. So a convenient measure of population growth is a doubling period. Hey, doubling. The population of the world was 6 billion in 1999. This population seems to be growing exponentially and doubles every 35 years. So one more time. The general form of an exponential word problem is y equals a times b to the x. But to give you the doubling formula, so the previous example was half-life formula, the doubling formula, and again, you can see from my handout, notice our base is 2 for doubling, and it's still going to be the time divided by the doubling period that's provided. So that is the formula that we're going to use. And again, you can see the formula on that extra handout. It might uses C or M, where C is the initial amount and M is the new amount. Excuse me. So the population is probably going to grow. And some people get kind of caught up with this. So with this two-part problem, estimate the world population in 2050. Now, our reference is actually from 1999. So let's just talk about things. First of all, our A value, our initial population that we know from the recorded information, because we don't know the original amount of people at the beginning of time, but in 1999, there were 6 billion people. Now, we're not going to write all those zeros in, but we'll work in billions. The time frame, though, I think everyone agrees, is 2050 minus 1999. How many years is that? Well, that's 51 years. And of course, this represents T. What's our doubling period? Well, our doubling period, notice, it is doubles every 35 years. So when we plug this information into our formula, y is equal to a, 2 times 2 to the t divided by d, we'll get y is equal to, for this is question A, by the way, 6 billion, that's a 6, times 2 to the 51 divided by 35. Pause the video if you want to try it yourself. Now, this 51 over 35 is not a nice number. Notice, it's a long number. So I'm going to use first 2 to that answer, which is the 51 over 35. That's what that means. It's going to be kind of a number there. And then we're times it by 2, times by 6. So our answer is, oops, I should go back in black. Sorry about that. 16.473. I'll just say 47 if that's okay. And this represents billions of people. So in 2050, there will be 16.47 billion people. That's a reference, of course, right? So that's how we set this up. For question B, though, notice, when will the population be 24 billion? For this question, this 24 is our y. So what are we going to do? Well, we're going to set this up like so. 24 is equal to, according to our reference in 1999, 6 billion times 2. And all of a sudden, we realize our t, oops, hopefully you guys can see that t is being divided by that 35. So how are we going to do this? So some of you might remember the lesson. That is why I try to explain to you. When solving exponential equations, we're trying to get the same bases. So what should we do first? Pause the video if you're not too sure. We undo this by doing reverse BEDMAS. So we can divide both sides by 6. We divide both sides by 6. Notice we get 4 on the left-hand side, and we get 2 to the t divided by 35. Notice you all should be able to do this now. 4 can be written as 2 squared is equal to 2 to the t divided by 35. And when the bases are the same, we can equate their exponents. 2 is equal to t divided by 35. Move that 35 to the other side. And what do we get? T is equal to 70. So to answer this question, when will the population be 24 billion? In 70 years, the population will be 24 billion. Which really means, and I'm running out of room, 1999 plus 70 is equal to 2069. And again, hopefully that made sense. If you have any questions, I'll try to answer them on Friday. Try to show my face. Let's show my face. Stop. Show my face. Stop sharing. Hopefully that made sense, everybody. And again, I'll see you on Friday, where we can take a look at more of the questions about exponential word problems. I do recommend you try to do the first 10 on that page. Just ignore any of the homework on the actual handout page that I gave you. That's from a different textbook called the Addison Wesley book. Anyways, thank you so much for joining us. And hopefully you got something out of these 5 examples. Obviously, I'll post these answers so that you can all see it. Have a nice evening, everybody. Take care. Bye for now.